Okay, let's begin. Welcome back, everybody. We are right in the middle of this conversation about MCMC. We've gotten through Gibbs sampling. I'll remind you what that is. And we're going to be talking about Metropolis-Hastings that is a little bit more general purpose, and a little bit more nimble. I should point out, it's unclear which algorithm to use in all cases. And I'll talk about all the different issues. So if you can sample from all full conditionals, it's very tempting to just do Gibbs, but there can be reasons why you might want to layer in a Metropolis piece into your code. We'll talk about some of those issues. I think usually you just want to experience this at first. So I built in some problems in the homework, and I'll say a few things about that in this lecture too. There's going to be a proof as to why Metropolis-Hastings works. And the proof basically centers around this equation right here. If you thought about this as a conditional probability of theta, so I'm kind of thinking of theta as just my random variable. For Bayesians, usually we're moving around the parameter space. So we do a conditional flip, but these are just random variables in general. So if you're thinking about theta, and theta prime is two points in a space that you might be moving through. So theta is just one point in some space, and theta prime is some other point in the space. So we're talking about Markov transitions in this whole conversation. So this is going to represent the transition probability of jumping from theta prime to theta. So where in our space are we moving to? And this right here is the reverse, right here, moving from theta to theta prime. If you're thinking about these as conditional probabilities, this equation just kind of makes sense to you. So this would be the marginal probability of theta prime. So I'll just write this down. So this is just a conditional probability. And this usually we call the margin. I.e., what's the probability that we're at this point in space, theta prime? If everything was everything was continuous. Sometimes that happens. If everything was continuous, this would be a density, and these would be density functions. If everything was discrete, then these would be mass functions. So this is the marginal probability or density of being at theta prime. This is the conditional. And this is the conditional in the reverse direction, and this is the margin for theta. This would be just a standalone equation that you're used to seeing. It looks a lot like this. Probability of A given B times the probability of B is equal to the probability of B given A times the probability of A. So it has this same form. And you're going to think you understand this instantaneously. And you basically do. In MCMC land, or in Markov land, we usually will call this thing right here the transition. So you can think of it as a transition density or a transition probability. So it's the rate at which you move through the Markov chain. But it basically has the same form as this. And this right here is known as the stationary distribution. So we changed the words a little bit. But in just non-Markov realm, this is an equation you already understand. And so at the end of the day, this is just the rate. I'll just write this down. Some other function. I'll use rho again. This is the joint of theta prime in theta, and this is the joint of theta in theta prime. In Markov land, things are a little different than just having independent random variables. I'll write this bigger over here. So I just wrote down the joint of theta, theta prime, the joint of theta prime and theta. And that would be very akin to just writing down the joint of probability A and B is equal to the joint of probability B and A. There's a little bit of a nuanced difference. If you're just thinking about random variables that are exchangeable and it doesn't matter which order you see everything in, this equation is something you learned a long time ago. And so these are just fundamental rules of probability that we all understand at this point. This is going to be a little bit different because this is implying an order in which we see things happen. And so if the order doesn't matter, we call the chain reversible. So the direction in which you transition through the Markov space, it doesn't matter which direction you're coming through. The confluence through is the same in both directions. So we're going to not talk about reversibility. That's the part that I'm going to sweep under the rug, talking about exactly reversible Markov chains, because there's a lot of technical nuances. What we're going to focus on is showing in our algorithms that the stationary distribution is the target that we want to sample from. So in our case, our example that we were looking at last time, where we had these trace plots that were kind of evolving through space right here. We're moving through all of this, and then eventually we get somewhere. I'm going to zoom in on this. Zoom in. We'll zoom in right there. Maybe not. Anyway, if I zoomed in, it looks like this, right here. And that's what we saw last time. I want to just point out, at stationarity, the Markov chain is supposedly reversible. So, but when it's not stationary, i.e. you're still burning in, the path isn't the same all the way through. You can see this clear non-reversibility of everything. I don't want to talk about all that in this class. There's too many details there. What we're going to focus on is that once everything converges, it eventually converges to a stationary distribution, and that stationary distribution is the target that you want to sample from. So what I'm trying to say is, you are familiar with this idea, but there is a small nuance in there that I don't want to go into because I need to teach you a week or two of Markov chain theory. So we're going to forego that. Okay. Let me just remind you, a few reminders just about the logistics. We have a review session tonight. We're going to keep that review session. So there is a homework extension 1 week. And so I can understand that you guys might be thinking, well, I'll just put everything off for another week because I've got the extra week and I'm not going to pay attention to this review session. I'm going to beg you for a review session next week. I can't do it, is the problem. So next Wednesday at 5:30, our department has a big event going on. And so I've got to be there for that event. So hopefully everybody in the stats department are going to be there as well. So it's the award ceremony for corporate partners, big reception. One of the funnest things we do. Saying that, we have a midterm exam on the 27th, so 2 days later, and I do want to give you guys a chance to do a review. So what I'll probably do is on this Monday, right here, I'll try to do a review. And so you can ask more questions. What I usually do right before an exam is something called yes, no, maybes. If you've taken my classes before, you're familiar with that. And so a long time ago, I got really tired of people asking, is it going to be on the exam? And it's a frustrating thing. Is that on the exam? Do I need to know that? And so I've decided instead of being frustrated, I'll just answer your question. So I'll either say yes, I'll either say no, or I'll say maybe. So I'll make 3 columns on a board, and it's up to you guys to ask. And I'll try to fill out the columns in a reasonable way that I'm not putting everything in the maybe category. So, but I will put a few things in the maybe category. So what I'll do by the Monday is write the exam, and I have contenders as questions. And if it's a contender for the exam, then I kind of was like thinking and quibbling, do I put this question or this other question? That would be in the maybe category. So it's pretty limited in the first place. It'll be like 5 or 6 things. But I'll let you try to guess and understand all the stuff you need to know. We'll do that probably on Monday the 25th. I'll try to get a room for it. Again, if you can't make it, I'll film it. And if you have questions and you want to know, you can ask them on Slack. All I ask is that you ask a real question. So, okay, hopefully that's reasonable. It'll get you through and all prepared for the exam. Okay, let me just turn this off for a minute. I'm going to remind us what Gibbs sampling is. And I'm going to remind us through an example. So example, this is one on your homework. Let's say xi are coming from a normal distribution. This is what I concluded with. There are a few questions about this after class, so I think it's worth going through in a little bit more detail. So you see a whole bunch of data. You'll simulate this data. So you simulate your own data, you know what the truth is, and you make sure you converge to the truth. And then if everything works out in your simulated examples, you can go ahead and use your code for examples that show up in your research. So this is what the Gibbs sampler looks like. Gibbs for pi, mu, phi, given all of your data. And I'm going to assume what our priors are. I'm going to pick pi mu to be proportional to 1, and pi phi is going to be proportional to whatever phi. And so the joint posterior distribution is proportional to phi to the n over 2 minus 1 e to the minus phi over 2 sum of the xi's minus mu squared. And so on a previous homework, I had suggested you sample from this, but we didn't know how to do it. What is the joint? And now we've seen the joint. It's that triangular distribution. We'll play around with this code a little bit more towards the end of class. And remember this triangular distribution that we got? I only have like 20 data points, so there are only 20 x's. We'll see this a little bit later. As n goes bigger and bigger and bigger, that triangle starts to become rounder and rounder. Okay, so the edges start to go away. And so if you're worried about maybe things you've done in the past, where you ended up maybe knowing that s squared, a good estimator for sigma squared, and x bar are independent of each other in the normal case, and they're only independent in the normal case. So that's an if and only if. Those statistics are independent, but these parameters are not independent. And so there is a dependency between those. And so you might be thinking, well, in classical land, I just treated those as independent, but there is information between them. And you can see it just from the likelihood function. And so a Bayesian has a little bit of an advantage in quantifying that dependence. But if n were big, then maybe it doesn't matter. And that's what we'll see. But if n were small, it kind of matters. And so quantifying that uncertainty is really important. And I think a Bayesian can do that just a little bit better than our counterparts. Okay, so the Gibbs sampler looks like this. So this is going to be an iterative algorithm. I usually index by t, so I usually use the metaphor time. And that's just my iterations as I step through the Markov chain. So for t goes from 1 to t, I'm going to update mu. It's going to come from pi mu, given phi t minus 1, and our data. So this is the full conditional distribution for mu. I'm going to update mu there, and then I'm going to update phi. And it's going to come from its full conditional distribution. I'm going to update this t that I just got right here. So all of my full conditionals are conditioned on my most current draws. Jenny and I were having a conversation after class. This, if you know about linear systems and iterative solutions for iterative methods for finding the solution to linear systems, you might be familiar with the Gauss-Seidel algorithm, and this really smacks of it. But the mathematics used to proving convergence is very different because that's converging to a point where our thing is converging to a distribution. And so instead of studying contraction maps, we study what's called detailed balance. So different branch of mathematics, but the algorithms are eerily similar. So just as a reminder, this thing right here, that's going to be a normal distribution. We worked this out in the first week of class. Given its normal distribution centered around x bar, and it's going to have precision parameter phi t minus 1. And so this is the variance of everything. I've just flipped upside down the variance parameter. And the only reason I do that is because I like working with gamma distributions instead of inverse gammas. So it's an arbitrary convention. So what we're doing is we're just taking mu t and we're drawing from this. So you just do one draw from a normal distribution where you know its parameters. Again, we're going to have to initialize that at the first step. And so I should probably write down the initialization. Initialize P0. And it certainly matters. If you're far from stationarity, it's going to take longer for you to get there if you're very far away. Saying that, I want your code, when you write your code, to be robust to starting conditions that are really, really far away. They present numerical issues. In real problems, we don't know where the mass is concentrated. And so we can't have all these numerical problems in our code. Phi t, this one, this fault conditional is going to be a gamma distribution. This is gamma n over 2. And then this is going to be s squared right here. But that's going to look like this. So I'll just write down xi's minus mu t squared. This is going to be over n. So this is s squared, and it's going to be divided by 2. If you look at the expectation of this thing right here, it's going to be this over that. So the n's cancel each other. Oh, sorry. This n isn't there. So it's ns squared. So the expectation of this thing is that over that, which looks like the inverse of s squared. So we'll just update pt with that. So if you're using R, MATLAB, or even Python or something like that, they have built-in generators. So you can invoke the gamma generator. In MATLAB, you write the command random, and then you tell which distribution it is. You put in the command gamma. In MATLAB, for this, I usually use what's rand n. So, but you can use the command random and plug in the term normal, and it'll know how many parameters you need to input for it. So if you ever need help on that, you type help into the command window, and it'll tell you all about the distribution. So anytime you go and you use a built-in generator, go visit the help file and make sure you've understood how they parameterize this distribution. I'll give you a hint. In R and in MATLAB, by default, they flip this thing upside down. So you have to be careful. So again, arbitrary convention, but you got to know what they are. So that's potentially going to save you 20 hours of trying to debug something where it's not really a bug. You just didn't understand the command you were invoking. Okay, so that's what Gibbs sampling is. And Gibbs sampling is kind of cool that it breaks up this two-dimensional problem, two-dimensional sampling problem, into two one-dimensional sampling problems. And what we've at least described in our code, our example, that this thing eventually converges to the joint distribution of mu and phi. And so early on in the draws, so for small t's, if you started very far from the stationary distribution, it takes a while for it to get there. And then once it gets there, it stays there. So if you ever are programming something up, and you're like, it looks like it converged, but then it stopped being converged for a second, that is guaranteed to be a bug. So once this thing converges, it stays converged in the strongest sense. So if you know a lot about convergence, it doesn't jump away. It jumps away only on an unmeasurable set, but in discrete land, that means it never happens. Okay. So just a few reminders. Metropolis-Hastings is an algorithm that you can invoke when you don't know how to sample from the distribution. And you've got a lot of flexibility with Metropolis-Hastings. So let me tell you about that now. I guess I should ask, any questions before we proceed? Good. Okay, Metropolis-Hastings. IEEE says this is the #1 algo of the last 100 years, so it's not just me that likes it. This is my favorite algorithm as well. Just out of curiosity, do you guys have favorite algorithms? You should. You should have ones that you really like for problems that you really like, and there should be reasons behind that. So out of that IEEE list, can you guys think of any other algorithms that were in there?
Sort.
Quick sort. So is that what you said in the back?
Yeah.
Quick sort. Yeah, that one's pretty cool. So if you know how quick sort works, I kind of like that one. I kind of don't really like sorting algorithms, simply because when I took my data structures and algorithms class, you spend like a month sorting stuff. It's like, it's kind of cool. You learn different data structures, you learn some math, you get some implementation skills, but it's kind of a boring problem. So it's like you start with bubble sort, and then you can figure out that you can do it a lot faster. So and not do a linear sort time, but you can do it logarithmic time. I guess that's cool. Any other favorite algorithms out of that list? FFT, fast Fourier transform. I really like that one. So your signal processor, I imagine?
Or mechanical computation.
Okay. Okay, well. So FFT is pretty cool. So if you don't know about it, go check it out. It's probably my 3rd favorite algorithm on the list. So my 2nd favorite algorithm is simplex. So, and the reason I like simplex is because it gives you more than just the optimum answer. It tells you if I change things, how much would affect the optimal answer. So you get 2 pieces of solution, and I kind of like that. This algorithm, it gives you kind of everything. It lets you know the interaction between parameters, it gives you probability distributions, sampling scheme that I can kind of do everything with. So this is the savior to Bayesians. So fun thing to think about is just what algorithms do you like and why do you like them? You should probably have a favorite theorem as well. So be thinking about that. Okay, here's what the algorithm looks like. So we're going to initialize. Oh, and let me just write this down. It's just a general goal. So our goal is going to be to sample from, I'll write it down as this joint posterior distribution. And I'm going to show you a couple different strategies for doing this, but I'm going to show you what's called the block Metropolis-Hastings Sampler, where I update everything together in one step. So as a counterexample, we're updating things in 2 steps, not as a block. If I try to update both mu and phi together, that's what I mean by block updating, where this would be sequential updating. So I'll show you a couple different strategies, but this algorithm is very flexible where you can do a lot of different stuff with it. So we're going to try to sample from this, and I'm kind of thinking that this is high dimensional. So maybe theta 1, theta 2, theta 3. That'll at least get the induction going where we can extend to everything else. So theta 1, theta 2, theta 3. So we'll just talk about it a little bit more generally. Here's what the algorithm looks like. So first step, to initialize. So I'm going to initialize my joint set of parameters. And it doesn't matter if these are scalars. This could be a scalar, that could be a vector, this could be a matrix. Maybe this is a tree or some topological space. Just something that's a random variable. So lots of flexibility. So we'll initialize first, start somewhere. Again, if we start very far from the stationary distribution, it'll take longer to run your algorithm. And here's what it looks like. There's only 2 steps. Let me write it over here. Same sort of iterative setup. But there's going to be 2 steps here. So the first step, and this is probably the big question, is how do you pick the proposal function? The first thing we're going to do is we're going to propose. We'll write it down like this. Propose. And I'll talk about this step in more detail, but this is the whole question, is how do you keep this function G? So this is going to be some proposal distribution. And I want to point out, you usually build this up in a Markov fashion. So you're going to do something with your current location, and from your current location, you're going to propose to move somewhere. Okay, I'll talk about that in more detail, but this is how all MCMC algorithms differ, essentially, is in your selection of G. And there's a lot of strategies, and we could fill a whole class with different strategies for different complexity of problems. So, and this is going to be your decision. So your decision, and I usually call this the Metropolis-Hastings decision rule, it's going to choose between 2 things. You're either going to stay at the same location, or you're going to make the move. So, and that's going to look like this. So there's going to be an acceptance probability. I'm going to flip a coin and I'm going to make a decision whether or not I make the proposed move or I stay in the same location. So this is going to be the minimum between 1 and this thing right here. I'm going to call this, I'll name it in a second. So this is going to be pi theta star compared to pi theta where we previously were, t minus 1. And then I'm going to account for my proposal. That has to come into play right here. Looks like this. G theta t minus 1. It would be theta star. So just to be clear, this thing right here, this is likelihood times prior divided by its normalizing constant, and this is a likelihood times a prior times its normalizing constant. So let me just write that out real quickly, what these things look like. This is going to be the likelihood of theta star given x. So the caveat is I have to be able to write down the likelihood function. And for our example, we can do all of that. And I have to be able to write down my priors. So for my example, I can do both of those things. And then I normalize it. Integrate likelihood times prior, d theta. And then I'm going to divide it by something similar, but I'm going to evaluate it 2 different places. T minus 1 given x, pi theta t minus 1, and it's going to be divided by some normalizing constant. Now, I'll point out to you, if you could actually do the integral, you already know how to sample from everything. If you can integrate over the space, you can do everything you already want. So what we're going to try to do is avoid the integrations in the first place. And so that's where that algorithm is helpful. The nice thing is that these cancel. So So I don't need to actually plug in my target posterior. I can plug in an unnormalized version of it. And that's a beautiful thing, that I don't need to normalize the distributions. I don't need to work through any intervals up front. And the same thing is true for G. I need to be able to evaluate the kernel of G for this to work. So I'll give you some choices for that in a moment. So are there any questions about this step, just computing this probability? So I'm just taking the likelihood, plugging it in here, multiplying by its prior, plugging in those values. So that would be this thing right here. That's all I need to evaluate. I can write it down, and I can write this down, code it up, and evaluate phi and mu at different places. And those different places are phi and mu star versus phi and mu t minus 1. Okay, so that's what we do. We compute this number. This number is going to be between 0 and 1. So we'll talk about that in a second. It's always thresholded at 1. This is guaranteed to be greater than 0 because they're all density functions or mass functions. So something positive. And then we're going to make our decision. So I usually write this down as step 3, but this is really just a coin flip. So I'm going to make my decision based off of this probability. So I'm going to update theta at time step t, and that's going to be one of two things. I'm either going to move to my proposed location, or I'm going to stay where I'm at. This is going to happen with probability alpha. And this is going to happen with probability 1 minus alpha. So this is just a Bernoulli coin flip. So I have a Bernoulli generator. I flip a coin. If it lands on heads, then I move to my proposed location. If it lands on tails, I stay where I'm at. I want to distinguish that from accept-reject samplers where you throw the sample away and you pretend like you never saw it. You don't do that. You stay at the same location and you store it. So that's absolutely necessary for this thing to work. So you're never going to throw anything away, at least in this basic sampler that I'm telling you about. There is something called thinning, but in spirit you're not throwing anything away. So we'll talk about thinning a little bit later. So that's the algorithm. And this is one of the things I really like about this algorithm, is I look at it, it's just eerily simple. I make a proposal, I've got some G, and then I decide whether I want to go to where I proposed using this rule. And so this right here, I usually call the Metropolis decision rule itself. So we need to study that rule. Why is this working? Stephen?
So you said that this is presupposing that we know the likelihood, right?
Well, you know the likelihood, right? You can write it down. In every problem I'm ever going to give you in this class, you can write down the likelihood.
But we don't know pi of theta given to the data. That's what we're trying to sample from, right?
You want to sample from it, but you can evaluate the kernel of that distribution. Totally different things.
Okay.
So just because I can evaluate something, so let's just say I've got a normal distribution, right? I can plot it for you. How do you sample from it?
Okay.
It's a different problem.
Yeah.
So I think that I hear this confusion all the time, but evaluating a density at a point, so that's just I can plug everything in and I get some scalar out, and some number between 0 and infinity. If it's a mass function, my evaluations are between 0 and 1, but densities can go bigger than 1. So being able to draw the normal curve and sampling from it are different things. Okay, let's look at the rule. Let's just at least try to intuitively figure out if this kind of makes some sense in what it's trying to say to you. This is the minimum between 1, whatever my target is. This doesn't have to be a posterior. It could be any distribution where you can evaluate its density or its mass function. real quickly, the proposal itself is Markov. It could be an independent thing, but it doesn't depend on samples that we saw 2 iterations ago. So our proposal is Markovian, and this whole algorithm is Markovian. So if I look at it, I'm only using where I previously was to make my transition. So I'm not looking at samples before that. So this algorithm is a Markov chain. And so what I'm going to teach you, probably not this time, is that if you run through a transition matrix over and over and over again, it will converge to some probabilities and being in some locations. So it'll eventually converge to something. And we'll simulate that in a future class. That's called the limiting distribution. They don't always exist. Markov chains do, however, always have stationary distributions. And if a limiting distribution in a Markov chain exists, it is the stationary distribution. And so what the algorithm is doing is it's marching through this Markov chain and converging to its limiting distribution. And its limiting distribution is the stationary distribution. And in our case, what this algorithm converges to is sampling from the posterior distribution. So the stationary distribution of this algorithm is this thing. So that's what this algorithm is accomplishing. So that's our goal. That's why I've told you this algorithm, and it accomplishes our goal. Same thing's going to happen where this is an eventually sort of thing. It doesn't converge on the first step. You have to run it for a long while, plot everything out, and see that everything is converged. Look at the trace plots. Okay, so this is a Markov chain. I just want to look at this right here. So this is 2 different chunks. So I'm going to look at this first piece, and then I'm going to look at this second piece. What I want to point out, first of all, is that our proposed thing is in the numerator and the target, and then our previous time step is in the denominator, and everything is flipped upside down here. So again, the random variable for G is the thing over on the left-hand side, and this is what's conditioned on. So the random variable appears in the denominator for the proposal, and it's in the numerator for our previous time step for the proposal. So this is the ratio of targets. This is the inverse ratio of proposals. So if we forget about this just for a second, the proposal, what we're really looking for, if we're going to accept, is for whatever this number is to be big. So big numbers lead to acceptance. So if I just focus on this part for a second, I can kind of see that, well, this thing's going to be big, and it's going to be bigger than 1 if this density function right here, for our target, has higher mass for where I'm proposing to than where I previously was. So again, I can evaluate this function. So if I look at whatever this complicated distribution is that we're trying to sample from, I'm just going to draw it in 1 dimension, because I can't draw in 3D very well. But if I was here, and then I propose to move here, and it's higher, I'm inclined to make that move. So because I've just proposed something that's farther into the mass of the distribution. And so it looks better than where we were at. And so we want to move there. Sounds good. That makes sense. This is the opposite. This is the be careful step. So this says, well, we want to make sure that we can move backwards. So in our proposal, this is determining how we're going to move from our previous time step to our proposed location. And this is the reverse direction of that. So what it's saying is that if it's very hard to get back to, I'll say it this way in the numerator, if it's very hard to get back to where you're coming from, maybe don't make that move. So what I mean is, if this is small compared to this, be careful. So what this is saying altogether is, think about the move you make. If it improves things, you're inclined to make it, but you also want to be able to come back to the previous location. This is one of my favorite life principles. So when I see this algorithm, I think about my own life. I think about, I'm always transitioning through life. Maybe it's Markovian, we can imagine that. Einstein says everything is Markovian. I'm not sure there's a proof on that. But it's some discretization, maybe it is. So I think about moves that I'm making, and if I make the move and it looks like it's going to improve things, then I'm inclined to do it. But I need to make sure I can come back to my previous location. So let me give you a couple examples. If I went, so I've worked really hard in my life. I became an assistant professor. I got tenure some number of years ago. Things are going pretty well. If I went to my department head and said, hey, Dave, you know, I want to take the year off and I want to go try out a new stint. So I want to become a professional motorcycle racer. And so I think I got it. You know, I was riding with my friends and I was a little bit faster than them. So I think I can make a career out of this whole thing. And so, and probably for that year, it would be a lot of fun. I've got a little bit of savings. I go out to the racetrack and I go there and I'm having a great time. But then everything doesn't go so well at the end. And I come back to Dave and I say, hey, can I have my job back? You know what the answer will be? No. I can't go do that for a year. I can't take a sabbatical and figure out if I'm going to be a talented motorcycle racer. I already know the answer to the question. I'm not very good. So good enough to be there, but I could never make any money doing it. So I need to be careful. Let's think about another example. Maybe this relates to your life. So Friday night, your friends ask you to go out and say, let's go to the bars and spend all our money. So maybe do some gambling as well, and you have to think about the repercussions. Maybe that sounds like a lot of fun for 15 minutes or a couple hours, but then Saturday morning arises, and you forget about all your obligations. And so you've got to be careful when you make moves. Just because it seems like fun for a second, you've got to be careful and make sure you can return to your previous state. And I think we all understand that. That's what this algorithm says in a probabilistic sense. Is make the move if it looks better than where you previously were, but make sure that you're able to go back. So don't burn any bridges. Yes, please.
So the whole point of this is that you don't know the posterior pi of get a given x in closed form, right?
You don't know the normalizing constant, but you know the kernel.
So you can, that's why you can evaluate.
That's right.
Okay.
So you can evaluate it because it comes in the form of the ratio. And almost all, except reject is a counterexample to this. But most sampling algorithms, the target comes in the form of a ratio. And when it does, that's a really nice thing. So because you can usually evaluate that. So there are classes of MCMC algorithms where you don't have to evaluate the likelihood or the prior or the kernel of the distribution. We're not going to talk about those. So in every example that we're going to study in this class, you can do the evaluation. So what you don't know how to do is sample. You can just evaluate the function, which are different things. Warren?
Could you draw a picture of an example where it'd be easy to get to, but not easy to get back? Like for this example right there, it looks like if you made that move, it'd be pretty easy to get back.
So I'll point out, I'll show you a couple different strategies. I know you want to know all about G right now. So let's just look at a couple different Gs and talk about different examples. So G doesn't have to, this conditioning right here doesn't have to occur. So I could just come up with some distribution. This is a random variable for theta t minus 1, and here's a random variable for theta star. You actually don't need this conditioning right here. And that's where I could answer your question. So let's just look at the independent case. So independent proposals. So this is G theta given theta t minus 1 is equal to G theta star. Okay, so the conditioning doesn't have any impact on the distribution. And you can do this. So if you plug an independent proposal into this algorithm, theoretically it works and eventually it'll converge. So, example. G theta. I'm going to think about this as a one-dimensional example, but you can butter this up and make it pi d if you want. I'm going to say this is a normal distribution. So let's just imagine for a second this is 1D. So let's say this is mu. I'm going to center it at 0 and give it variance 1. So why did I pick that? Arbitrarily. This would be a bad idea in a lot of cases. So that just looks like this. Centered at 0, and I have variance 1 right here. So if theta star was here, and maybe theta t minus 1 was way over here, this would be a bit of a problem right here. This is in a low probability area. Let me draw on here maybe what the target looks like. So I'm going to say this is G. And this one right here is pi. About the same as what I drew before. So here's one where I propose to somewhere, right here. The proposal looks better than it did before. The target actually looks worse. So there's this balancing act. So this is something where I might not want to go there because there's no mass in the target, but the proposal is higher. Let's imagine I had something like this, where this bump, let's put this over maybe, let's change the example a little bit. Let's say this right here was theta t minus 1. And let's say this right here is theta star. Right here. So this would say I'm moving to somewhere that looks like it has something about the same mass in the target, right here, but the proposal value is way higher over here than it is over here. So while the target might be about 1 in this ratio, here's an example right here where it's going to be harder to move back. And I could make this more extreme, where this is very far in the tail, and it would be hard to get back into that location. And that's because this is an independent proposal, and it's just not centered in anywhere reasonable. So here's at least an example. Let me show you an example where the proposal washes out of everything. And we'll come back and we'll pick up with this next time. So here's a Markov proposal. And this is probably the most common proposal that people use. So G theta star given theta t minus 1. This is going to be a normal distribution. I'm going to center it at theta t minus 1. You could even think of this as high dimensional in this case. And I've got some variance in here, psi. If you wanted, I could make an identity matrix if this were high D, but you can continue to think about this in one dimension, right here. What this does is it centers everything at the previous location, right here. So this density function looks like this. 1 over 2 pi psi e to the minus 1/2 theta star minus theta t minus 1 squared over psi squared. So this is a Markov transition. So what I'm going to do is I'm going to center my proposal where I was last time. So this is kind of the philosophy of what have you seen lately? It must be pretty good. And I'm going to center my step right around it. So I'm going to say I'm going to look kind of to the left or to the right. and I'm going to have some tail fall off that's governed by a Gaussian distribution. The beauty of this right here is that this is symmetric in both of these terms. If I flip it around, it's the same density function. And so if I ended up using this proposal, this thing right here in the decision rule is actually 1. And it cancels. So it's just as easy to move back and forth. So that's kind of nice. It has this symmetry. Where this goes really bad are on things like multimodal distributions. So you're always going to center everything where you previously were, but you might want to make some very big jump across space. Let's come back next time, talk about proposal strategies, because this is the whole thing in Metropolis-Hastings. So the fact is that so long as G covers the same space that pi covers, regardless of how you select G, your algorithm will converge eventually. However, you might have to wait a very, very, very long time. So we want G's that kind of can move to the mass where pi is at. How do we come up with that G? You have to tell me what pi looks like. And I have to think about what our target looks like for a while to come up with a good strategy for G. Let's pick up with that next time. Thanks, you guys. Review session tonight, so I'm sure there's lots of questions. Again, if you can't make it, please post to Slack.